हेलो बच्चों। तो आज का हमारा टॉपिक है रेजोनेंस। फर्स्ट ऑफ ऑल, व्हाट इज रेजोनेंस? इट इज़ अ कॉन्सेप्ट विच डिफाइंस द डीलोकलाइजेशन ऑफ इलेक्ट्रॉन्स। जो हमारे इलेक्ट्रॉन्स हैं वो कभी कभी कुछ मॉलिक्यूल्स ऐसे होते हैं जिनमें बिकॉज ऑफ द प्रेजेंस ऑफ पाई बॉन्ड एंड कंजुगेशन देयर इज डीलोकलाइजेशन ऑफ इलेक्ट्रॉन्स, और उस वजह से उस पर्टिकुलर मॉलिक्यूल को हम एक स्ट्रक्चर बना के उसकी प्रॉपर्टीज़ नहीं बता पाते, and that molecule have many structure which contribute to the actual structure. Okay, so let's start. So we will start with the definition. When a compound can be represented by more than one Lewis structure, an actual structure is a hybrid of all the structure, the compound is said to possess resonance. So resonance is the property, वो property है जो उन मॉलिक्यूल्स में प्रेजेंट होगी जिनमें डीलोकलाइजेशन ऑफ पाई इलेक्ट्रॉन्स होगा बिकॉज ऑफ द कॉन्जुगेशन. देयर विल बी मैनी स्ट्रक्चर्स, दो स्ट्रक्चर विल बी कॉल्ड द रेजोनेटिंग स्ट्रक्चर. द रेजोनेटिंग स्ट्रक्चर विल कम टुगेदर and will form hybrid structure, and that hybrid structure will depict most of the properties of that particular molecule. We can also give the another definition, that is, it is the concept where electrons are delocalized. We will understand this word. Firstly, let's go through the definition. It is the concept where electrons are delocalized over three or more atoms which can be depicted by which cannot be depicted by one simple Lewis structure. So let's come to this structure. Okay, this is the structure of, you can say, here we can see that carbon is present and two oxygen is present. This is carbon dioxide. Okay, this is the structure of CO2 molecule. Now see here we can draw this structure like that, and like this also, and that also. So we are able to make three structure for just a molecule. So here we can say that these are resonating structures. These are resonating structures. Okay, so here these are resonating structures, and you can see over here that there three bonds we are able to see, but these are not three actually. Here also you are able to see three bonds, but these are also not three actually. The structure we usually draw is this one, but somewhere because of the delocalization, because of the movement of pi electrons, it seems like this. Okay, so we can say that this is not the actual structure, and the actual structure is the resonating is the combination of resonating structure, that is resonance hybrid. Now come to localization and delocalization of electrons. So what is localized electron? Let's see. Electrons in sigma bonds have a fixed location. Electrons having fixed location are called localized. These are called localized and never move. Okay, if you are going through a structure, आप कोई ऐसा structure देख रहे हैं जो आपका रेजोनेंस शो कर रहा है, लेकिन अगर उसमें मान लीजिए ओके, दिस इज द स्ट्रक्चर. तो इसमें क्या होगा कि अगर कोई सिग्मा बॉन्ड है, कोवलेंट बॉन्ड है, दैट विल नॉट मूव, वो वहीं का वहीं रहेगा. जो आपका पाई बॉन्ड है उसका इलेक्ट्रॉन्स मूव हो सकते हैं, ठीक है, लेकिन सिग्मा जो बॉन्ड होगा उसका इलेक्ट्रॉन मूव नहीं होगा. नाउ कम टू नेक्स्ट थिंग, दैट इज delocalization. Now see here, conversely, pi electrons are referred to as delocalized because they can be easily moved around. So from here we get to know two things, that the sigma bond electrons are called localized electrons, and they are not moved while making the resonance structures, resonating structures. Next is pi bond electrons. The pi electrons are able to move around the molecule, and that's why they are called delocalized electrons. Now see here, delocalization of pi electrons in the nitromethane. You can see here, this is the single bond, this one is the single bond, and here it is the double bond. and it is in the conjugation of this thing. So what is happening there? This thing and this thing, this area of the molecule is participating in making the two structure, but this thing is intact, but the area where we can see the single bond, okay, here we are able to see the single bond, here we are able to see the single bond, it is intact. It is intact because the sigma bond electrons will not move. These electrons are localized, and here you can see the lone pair, okay, you are able to see the lone pairs. These lone pairs can move, okay, or the pi bond electrons can move. So you are able to see here two structure, okay. So how they are happening? If we will move this electron here and this pi electrons here, we will get this structure. So that's why there is this kind of arrow present. The double-sided arrow is present to show that this structure is equivalent to this structure. They differ only in the delocalization of electrons. Now come to features of resonance. What are, if we are talking about anything, even if we talk about a phone, a laptop, a car, we talk about the features, okay. So there are some features related to resonance also. Resonance structures are formed due to delocalization of electrons and not by changing the position of atoms. Let's go back to our example. Here we are able to see that structure. Again, see properly the structure of nitromethane. Here you can see that the position of the atoms, where N was present, it is exactly at the same place in the second structure. Where CH3 was present, it is exactly present there in the second structure, okay. O atoms are present on their respective places. If I will give them numbers, okay, if I have to give them the numbers, I am giving this one, 2, 3, 4, 2, 3, 4. So we can say the atoms 1, 2, 3, 4 are exactly at the same places where they are in the structure 1, in structure 2 also, okay. So we will not touch the position of the atoms while writing the resonating structures. Now come to the next feature. The delocalization of electron is shown by using curved arrows, okay. When you show the delocalization taking place, what will you do? You will use the curved arrow, okay. It will show that these particular electrons of a particular pi bond or a lone pair or a negative charge are moving from one place to other, okay. If I have to move the electrons here, how they will move? See, there is double bond and here is single bond in the first structure, okay. Here you can see one lone pair, 2 and 3. Here the lone pair which was present here will go here. What I am making here is a curved arrow, okay, and that double bond, it will shift there. So there will be 3 lone pairs. Previously there were 2, now there are 3, and negative charge comes and it moves from here to here and this becomes a double bond, okay. So this is how I will show with the help of arrow that these electrons are going there and we are getting this structure, okay. Now come to the third point. The energy of resonance hybrid is always less than the energy of any of the contributing resonance structure. How it is happening? Okay, see, what is the resonance energy? It is the average of the energies possessed by the various resonating structure, okay. So the resonance energy will be equal to the energy of resonating structure 1, resonating structure 2, resonating structure 3 by 3, okay. Since it is the average, it will be less than the energy of any of the contributing structure. Let's take an example. If first resonating structure's energy is 4, next is having 5, and next is having 6. Okay, so the energy of resonance hybrid will be 4 plus 5 plus 6 by 3, that is 15 by 3, which is 5, and it is less than 6, which was one of the resonating structure 3. Okay, so from here we will get to know that it is possible and it happens always that energy of resonance hybrid is always less than the energy of any of the contributing resonance structure. Why it happens? Because this energy is the average of all the energies of all the resonating structures of a particular molecule. Now coming to the resonance energy, the difference in the internal energy of the resonance hybrid and the most stable canonical structure. Here this word is written canonical structure. It also means resonating structure. Sometimes we call this as contributing structure also. So contributing structure, resonating structure and canonical structure are the same thing. So the difference in the internal energy of a molecule, okay, of resonance hybrid and the most stable canonical structure is called resonance energy. Now see, more resonance structure, more stable the molecular compound is. You have to always remember that the more is the number of resonating structure, more stable will be the compound. If there is a question and it is given that there is a compound A with resonating structure 2 and compound B with resonating structures 5, so which one is more stable? So the one which is having the more number of resonating structures will be the stable one. Okay, why it happens? Come to the next line here. More resonance structures contribute to the greater delocalization of electrons. Since greater delocalization of electrons happen, higher resonance energy is there and the compound becomes more stable. Okay, so these are interconnected. More resonance structure, greater delocalization, higher resonance energy, and the compound becomes more stable. Now see the resonance structure of benzene. Okay, this is the most common compound we discuss while discussing the resonating structures. Now you can see here we have made two structures. Here we have made two structures, but it is said that it have 5 or more resonating structures. So here you can see these are almost similar to each other. These are called resonating structures, and we can also say canonical structure or contributing structures. Okay, and the combination of this, okay, which is the actual structure. These are the structures. See, none of them, this is structure 1 and this is structure 2, none of them exactly defines the structure of benzene. Okay, when the experimental activities were done after the experiments, it was seen that neither this nor that defines the structure of benzene completely. Okay, so they have seen some few things in the experiment that according to this structure, benzene should contain 3 pi bonds. Okay, 1 2 3 3 pi bonds and 6 sigma bonds, because it is a hexagonal ring. 1 2 3 4 5 6, it should be there. But when we went through the experiments and when we have seen the data, it was completely different. okay, and it was in between that we got the bonds were not like this, okay, they were a little bit different. What was difference we have seen there is that the 6-membered ring in benzene is a perfect hexagon with all the carbon bonds having an identical length of 139 picometer. This is something shocking. How? Because we were thinking it is a 6 carbon ring, it should be like this, having 3 pi bonds. So pi bonds will be having the length different from sigma bonds. So we were eager to find out that this must be containing carbon carbon double bond equals to 134 picometer, because this is the experimental data we have for carbon carbon double bond, but this was not something we have find. Next we wanted carbon carbon single bond 154 picometer length, but it was also not there, okay. So it cannot look like this, because this is the structure which should be similar to this data, but this is not similar to this data. Now what happened, we got a length which is 139 picometer, which was intermediate between what thing, it was intermediate between the carbon carbon double bond length and carbon carbon single bond length. So what happened here, we got a bond length which was around 1.5 carbon carbon bond. It means the bond is more than the single bond and less than the double bond. So what we do, we normally make the structure of benzene like this. We make a ring and we imagine that every single bond have some partial double bond character, so it becomes like that, and it can be either shown like this. This ring shows the delocalization of electrons, which means the resonance is present here, and because of the resonance we are not getting these data, we are getting this data over here. So what we have seen, we have seen that resonance had an effect on the bond length, okay. Now come to this structure. I have already told you that sometimes it is told that benzene have more than 2 resonating structure. So these are the 2 structures we have seen in the previous slide. These are called Kekulé structure, which was proposed structure, okay, which are similar to each other, but they do not tell all the actual properties. Combination of them, which is the resonance hybrid, tells the properties. There was a scientist, Dewar, he also suggested some resonating structures for benzene, and they were like this, okay. There were 3 structures, let us name them. This is structure 1, this is structure 2. Structure 1 and structure 2 are Kekulé structures, and structure 3, 4 and 5 are Dewar structure, and the structure 6 is the hybrid structure for the benzene, which is the resonance hybrid of the benzene, okay. These structures are not we can say studied or taken for the detailing, because these contribute very less for the hybrid structure of benzene, okay. Come to the rules for drawing resonance structure. Whenever we are making resonance structure for a particular molecule, we have to keep few rules in our mind. First one is, all resonance structure must be valid with the Lewis structures, okay. There cannot be whenever we make Lewis structure, you know the dot structure, okay. If you are making it for the carbon, carbon have 4 electron in the valence shell, okay. Just like that, when you are making the structure for a particular molecule, keep the Lewis structures in mind. Next, all resonance structure must have the same atom, okay, same atom connectivity. It means if C is connected to C and then this C is connected to this O, this arrangement will be followed in every single resonating structure which you are making. You will not change the connectivity. You cannot change it to COC, or you cannot change it to like this. this is wrong. Okay, you will always write them in the same order. Atoms will have the same connectivity. Come to next thing. Yes, so all the resonance structure must have same atom connectivity and only differ in the electron arrangement. We were talking about the localization, so it is very obvious that we will let the electrons move. Electrons will only move in the resonating structures, but we will not touch the atom connectivity or the order of the atoms or the numbering of the atoms. Please keep that in the mind. All resonance structures have the same number of electrons and net charge. Okay, if there is a resonating structure which is having no charge on it, so all of them, see, net charge means the even if they have a combination of plus or minus. Let's move to one slide where we had that kind of, see, come here, you can see here the net charge will be same. Okay, you are able to see positive charge here. Since the electrons are moving from one atom to another atom, obviously charge will move. Okay, so here you can see positive charge, here you can see negative charge, here you can see positive charge, here you can see negative charge. So the net charge on it is 0 and net charge on it is 0. So the two resonating structures will have the same net charge. Okay, yes, formal charges on individual atom could be different, as I have shown you that the negative charge on one O atom shifted to the other O atom, but still the net charge of the molecule was 0. Okay, but the net charge, that is the sum of all the charges, must be same for the resonating structures. Always remember, you will not move the sigma bonds. Okay, never move the sigma bonds. Now come to conditions for resonance. See, every molecule cannot show the resonance. Okay, every molecule cannot undergo resonance. There are molecules which can tell their properties with the single structure. We don't need resonance structure for every molecule. Okay, but there are molecules which show different you can say many or a number of resonating structure which contribute to the hybrid structure. So which are the molecules which can show the resonance? Conditions for that are 2 pi bonds in conjugation. There is written a word conjugation. Let's understand this word first. Okay, conjugation means at the alternate position. Okay, if there is atom A, B, C and they are bonded like this, D, so it is at number 1, it is at number 2, it is at number 3 and it is 4. So if A and B having double bond, then leaving this double bond should be present on the alternate position. Okay, so 1 and 3 leaving the 2, such kind of arrangement is called conjugation. Okay, now see here, if 2 pi bonds are present in the conjugation in any molecule, then that molecule will show the resonance. See here, one example is given. Okay, here you can see this is butadiene. Okay, here if you will number it, leaving 2, 1 and 3 position are having double bond. So in this case sorry, in this case, when this double bond will move here, what will happen? Negative charge will come here, positive charge will come here. Okay, let me show you. If this moves here, it means the electrons will move here. Since electron moved, this is negative. Okay, and this thing will move here, so what will happen? Negative charge will come here and positive charge will come here and bond will go there. So if there will be this bond missing, the molecule would not have possessed the resonance. So we need 2 pi bonds. Okay, this is one condition. This is not necessary. If the molecule is not having 2 pi bonds in conjugation, that will not possess the resonance. there are many conditions, but one of those condition is if at the position 1 and 3, okay, I'm just giving the example, or we can say at this kind of alternating position leaving 1 in between we have pi bonds, then these are able to show the resonant structure. Come to next. Here next possibility is if you are not having, okay, just like the previous data, just like the previous one, we have seen in the butadiene at 1 and 3rd position we were having double bond, okay, at 1 and 3rd, and that's why that was showing the resonance structure. But if we are not having that condition and we are having the other condition, that is if there is a lone pair or negative charge and a pi bond in conjugation, then lone pair of electron or negative charge are transferred toward the pi bond. This is the thing you have to keep in mind, that if there is negative charge or lone pair, then it will go towards the pi bond, okay. See one example here. Here you can see there is only one pi bond. This is the pi bond. This is the pi bond, but it is having a lone pair in conjugation. Again see 1, 2, 3. So at the 3rd position it is having lone pair. So if first position was pi bond and pi bond condition in conjugation, the next is lone pair or negative charge and pi bond or pi electron in the conjugation, okay. So if this is the case, then also the molecule will show the resonance, okay. Come to the 3rd condition. If there is positive charge, that is called vacant orbital. Why it is called vacant orbital? Because positive charge comes when the electrons are lost, and if the electrons are lost, obviously orbital will be vacant, okay. So positive charge, the vacant orbital and pi bond are in conjugation. Now see, conjugation word you have to understand properly, because everywhere we are using this word, okay. So if the conjugation is present between the positive charge and the pi bond, then also the molecules can show the resonance, okay. See this example. Here also we can see the pi bond, and here it is in conjugation with the positive charge, and here you have to remember that you will transfer the pi bond, okay. Then the electrons of the pi bond will be transferred toward the positive thing. The pi bond electrons are transferred here to the positive charge or vacant orbital. You can see here you will transfer this thing to make the resonating structure, okay. This is how you will make the structure. In the previous slide we have studied about the negative charge and the pi bond, okay. Here the case is reverse. Here what you will do, you will transfer the negative charge or lone pair electron to the pi bond. Here you are shifting the negative electrons, and or we can say the electrons from the lone pair to the pi bond. But in case of positive charge it is different. From pi bond we are shifting the electrons to the positive charge, okay. Now next condition is if there is lone pair or negative charge and positive charge, okay. Here there is no pi bond. See, it can be the case if there is no pi bond. You cannot see the pi bond in this structure, but still it shows the resonance. So how it happens? Because here two things are in the conjugation, okay. What are these two things? It can be a negative charge or lone pair with the conjugation of positive charge, okay. Here you can see the lone pair or negative charge should be in the conjugation with the positive charge. Here you can see that. So we have studied in the previous slide, come to this, that whenever there is positive charge, the electrons from pi bond were shifted towards it. You can see from here, okay. Same happens when lone pair or negative charge is present. The electrons will be shifted to the positive charge or vacant orbital. See here, the electrons are going from this lone pair towards the positive charge, and see here we had lone pair and positive charge, and in the resonance, other resonance structure, automatically we are able to see the pi bond. And how we are able to see it? Because of the resonance. Okay, so in resonance, lone pair can convert to pi bond since single bond is present there, and because of these electron, the double bond is formed. And whenever double bond is moving, it will move as a pair of electron. Now come to next condition. The next condition is if there is free electron, that is radical, and pi bond in conjugation. Okay, here also you can see there is a pi bond and there is a radical. Radical means one electron, not a pair of electron but one electron. Okay, in such case the shifting is a little bit different. Okay, how it is different? You can see from here I have made such an arrow, not this one, only half. This arrow defines that only one electron is going from one place to the other. Sorry, if you are able to see this, there is double bond. Okay, while we are moving this, we have studied that we move lone pair towards the pi bond. Okay, so this is the electron, we will move it towards here, and from here what will happen? It will break, that bond will break, but the pair of electron will go in the different direction. Okay, see, you can write it this like this: CH2 single bond. I am writing that double bond as 2 electrons to make the understanding better. You cannot write it like that, but just for understanding purpose I am writing like this. Okay, now see, this was the radical present. Okay, now this radical is moving here, only one electron is moving. That was the double bond. This is the double bond. Okay, I am showing that double bond as 2 electron, and one of it will move here and one of it will move here. Now your structure will be, we will not touch the atoms, so we will write those atoms as it is. Okay, movement was there between the radical and this pi bond. Okay, so this electron will come here, radical. Okay, and this electron will go here, one electron. This electron come here, one electron. So can we define this thing, this 2 electron as a bond? Make it a bond. So what happened? We are able to find the another resonating structure. In case of radicals, the breakage will be a little different, and the arrows, you will not make such a curved arrow, you will make half arrow for the movement of one electron only. Okay, and this kind of structure you will not make. This is for only the understanding purpose. Now we have studied the conditions for resonance. Now come to this question: resonance structure can be drawn for, okay, out of these, for whom we can make the resonance structure? It is very easy, since the other 3 are possessing only single bond. Okay, and this one have a double bond for the conjugation with the lone pair of electrons. So our answer will be, our answer is going to be O3, and these are not able to show the resonance, and we are not able to make the resonance structure for NH3, CH3 and H2O. We are able to make the resonance structure for O3. See here, these are the resonating structures of O3. Here you can see that double bond and the lone pair or negative charge are in conjugation. So obviously this thing will go in the resonance concept and will show the resonance hybrid. Come to some guidelines which are necessary for drawing the resonance structure. Okay, to move electrons, only pi electrons and lone pair electrons can be moved from the higher electron density area to the lower electron density area. It means, see, simply we can say that when the lone pair was there and positive charge was there, so we were moving the electrons from lone pair to the positive charge, or from pi bond to the positive charge, or from negative charge to the positive charge. Why? Because these were the areas of high electron density and this is the area of low electron density. So always there will be the movement of electron, the pi electrons or lone pair electrons, from the area of higher electron density to the area of lower electron density. Pi bond can form another pi bond. Okay, as you can see in benzene, the resonating structures are like this, that this pi bond moves here, this pi bond moves here, and this pi bond moves here. So pi bond forms another pi bond. It can happen. Pi bond can form a lone pair, or lone pair of electrons can form a pi bond, as we have seen in one of the structures. Here we are able to see that this lone pair made pi bond here. Okay, so pi bond can be made by lone pair of electron, and a pi bond can convert into lone pair of electron. Now there are some contributing structures. Okay, you can see for the carbonate ion, CO3 2 negative, CO3 2 negative. If it is asked that CO3 2 negative can form resonating structures, yes. How? Because here you can also see there is negative charge, there is negative charge and pi bond in the conjugation. Okay, and the resonance hybrid is shown like this. This dot 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 means that this single bond is having partial double bond character, so its value is more than single bond and less than double bond. Okay, it is in between something, it is in between, let me write it again. It is more than single bond and less than double bond. This X is the value of this bond present here. Okay, its value is greater than single bond and less than the double bond. Now come to next question. How many resonance structure of N3 negative will be there? Okay, so here I have shown the image. Okay, so you can always do something whenever you are asked with the resonance structure, kindly mate them. There is no particular trick to remember the resonance structure. Once or twice if you will make the structures, you will get to know about it. Okay, so kindly if you will be able to see here, you can see the 3 structure. So how many structure N3 negative is having? 3 resonance structure it is having. Okay, this is one of the important questions. Now next, the number of resonance structure that N2 has. Okay, so it have only 2 resonating structure. As I have told you that you can draw ones, you can see here there are 2 resonating structures. Okay, one is like this. See, here is double bond, that is in the conjugation, and here reverse of that, reverse of one you can see in the structure 2. So there are 2 resonating structure of the particular molecule of NO2. Next, state true and false. All resonating structure must have same number of valence electron. Yes, it is true. Okay, we are talking about the delocalization, delocalization of electrons, but it doesn't means that electron went somewhere outside the molecule or it is not present there. Okay, it simply means the density of electrons is somewhere in one of the resonating structure it is somewhere else, and in the other resonating structure it is somewhere else, but all the valence electrons are present there. Okay, all resonating structure must have same number of valence electron because electrons cannot be created or destroyed by themselves. The structures you create must have the same number of electrons as the starting structure. the ending structure or the last structure or the middle structure or the first structure, all the structure should have the same number of electrons. Come to next, rules for estimating stability of the resonance structure. Okay, there are some rules by which we can understand that which resonating structure is more stable. There can be two resonating structure, there can be 4 resonating structure, there can be 5 resonating structure, but one of them will be more stable than the other one. So how we will get to know about it? See here, the resonance structure in which all the atoms have complete valence shells is more stable. If we have a structure where the complete valence shell of all the electrons is present and the other one where this thing is not present, then the first one will be more stable. Next, the structures with the least number of formal charge. It means that if we are having ABC, maybe some structure, okay, like this, and we are having ABC negative or positive, something like that, okay, so the one which is not having the charges or having least formal charges will be the stable one. The structure with the negative charge on the more electronegative atom will be more stable. If there is O present somewhere and there is another atom C present in a molecule, if the negative charge is on O, then that structure is stable. But if the negative charge is on O and positive is on, if negative is on C and positive is on O, then it will be not stable. There is the reverse also true. If there is some electropositive atom present, so plus charge should be there on the electropositive atom, then the resonating structure will be more stable. If there is an electropositive element and negative charge is present there, then it will not be a stable resonating structure. Come to last, the structures with the least separation of formal charges is more stable. If there are charges, if there is a pattern A, B, C, D, there is some molecule maybe, and A, B, C, D, okay, it is just an example. If this structure is like that, plus minus, and this is like that, plus and minus, so this will be more stable because there is least separation between the formal charges. Okay, so this thing you have to keep in mind. Now see one question. Write the resonance structure of CH2CH okay, indicate the relative stability of the contributing structure. You can see the contributing structures, okay, kindly observe them. If you are able to observe that this is the structure which is not having any charge separation, this is the structure which is having charge separation, and this is also the structure which is having charge separation. You are able to see this properly. Now see the other property, that the electronegative element is having positive charge on it. It means it is not that much stable, and here the electronegative element is having charge on it. It means this structure 2 is more stable than structure 3. This thing we concluded from here, and here we are able to see that there is no charge separation, and since there is no charge separation, it will be the most stable one. Okay, now see, the structure 1 is most stable structure. Why? Because each carbon and oxygen atom has an octet and no charge separation is there. There is no charge separation present in the structure 1. But in case of structure 2, there is charge separation, but negative charge is applied on the more electronegative atom, that is oxygen, and positive charge is on the more electropositive atom, that is on C, that is on carbon. Okay, so this is more stable than 3 because here the condition is different. We are able to see positive charge on the electronegative atom. So this is how you can identify which of the resonating structure is more stable and which of the resonating structure is less stable. Now see the number of resonance structure in ozone. Okay, these are 2. It will be better if you will try to make them. I have also shown the same structure in one of the previous slide. You can see here there are, see, the positions are same. Okay, there is conjugation between the double bond and the negative charge, and you are able to see this moving. Okay, thanks. I hope you liked the video. If you liked it, please come for the next step.